talk about acids and bases. And you should remember from when we were learning about nomenclature that we learned how to name different acids and bases. And so here I've included 3 examples of how to name acids. So the first one, H2SO4, would be called sulfuric acid. And the reason for that is because the anion sulfate ends in an ATE. When you have an 8 anion, it turns into an ic acid. For the second example, we have nitrite, which ends in ITE. When you have an ite anion, that becomes an OUS acid. For the third example, the anion is bromide, which ends in IDE. When you have an anion that ends in IDE, that becomes a hydrostem, here being brome, hydrostemic acid. And for us, acids were just compounds that were ionic that had hydrogen as the cation. That was basically our definition of an acid, and that still essentially is going to stand. So for bases, those were ionic compounds with hydroxide as an anion, and hydroxide has a charge of -1. The 2 examples that I have for naming the bases here are sodium hydroxide and calcium hydroxide. And I think these are definitely more straightforward than naming acids because you just name whatever the cation is and then hydroxide. The 2 here in calcium hydroxide comes because calcium has a positive 2 charge. So you need 2 of the -1 hydroxides to balance that out. Okay, and then before we move on, I just want to re-emphasize that we learned about solubility. And the first rule on our solubilities had to deal with ammonium and group 1A metals. So lithium, sodium, potassium, rubidium, cesium, and francium. Salts of ammonium and group 1A metals are always soluble, which means that if you have something like sodium hydroxide and you put it in water, it's always going to do what? Exactly. It's going to dissociate. If you have something with ammonium in it, like ammonium chloride, and you put it in water, it's always going to do what? Dissociate. Okay, so now let's talk about our new sort of classification for acids and bases. There's really 3 that we're going to talk about, but this is the first one. So we have Bronsted-Lowry acid-base theory. And the Bronsted-Lowry acid-base theory states that acids are considered molecules that can donate a proton. A proton is a hydrogen atom that has lost 1 electron, and we're going to call H plus protons. So an acid is a molecule that can donate a proton. A base is a molecule that can accept a proton. So we have acids are donating protons, bases are accepting protons. Seems pretty straightforward, right? And it is. So with that example, I want to introduce a new base. So we knew that any of the hydroxides were definitely bases, and that's still true, right? And based on this Bronsted-Lowry acid-base theory, our acids are still going to be true. So ionic compounds with hydrogen as the cation, that still works. Okay, but I want to add a new base in. So we have NH3, which is called ammonia. Here's the Lewis structure for ammonia. You'll see that it has, very importantly, this lone pair of electrons. And that lone pair of electrons on the nitrogen in ammonia allow it to snatch protons, just like the shark is going to do with the food that's right here. Right, imagine there's a cute little fish here. Oh, right? Beep. So the shark's going to snatch the fish. Here, the fish is a proton, and the shark in this example is the lone pair on the nitrogen, okay? So now we're considering ionic compounds with hydroxide as the anion, a base, and we're also considering ammonia, a base, because of the lone pair. Okay, so now here are some things that you must memorize. This is really important stuff. And it's not too bad. There are only technically 6 strong acids. They are the only 6 acids that we're going to talk about that you can actually say they're strong. None of the other acids are considered strong. And we'll talk about what that strong means later on. But these 6 acids that you need to memorize are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. And those are the formulas and the names. You need to have all of those. So these are the 6 strong acids. The only 6 strong acids that we're ever going to talk about. So what are we going to do with this? What do we do with acid-base chemistry? The first thing we're going to do is we're going to learn about acid-base reactions. So this is an example of an acid-base reaction. And we're going to diagram the reaction. And so on the reactant side, let's use the highlighter. You'll see that here we have our Bronsted-Lowry acid. And our definition for an acid is a molecule that can donate a proton. And if you follow this arrow here, you'll see that the proton's being donated to molecule B, which is a Bronsted-Lowry base. And bases are proton acceptors or hydrogen acceptors. So proton acceptor, proton donor. Okay, so here we have our acid, here we have our base. That's part of the diagramming. So we've said what the acid is and what the base is. Now, imagine that these arrows in the middle are just our normal arrows. So we'll just do beep. Normal arrow. And then look at the products on the other side. You'll see that molecule A no longer has its hydrogen. Molecule B now has that hydrogen. And you'll see that A now has a -1 charge. That charge, right, could be whatever the charge is on A. A is an anion. So whatever the charge is on that, that's what it's going to be. And then B gained that proton. Remember that protons' charges are +1, right? Proton has a +1 charge, which means that if molecule B was neutral and we added a +1 charged proton to it, the total charge is going to be +1. So all the charges balance out, and that's perfectly fine. So we've called these things on the product side different names. So you'll see that what was the Bronsted-Lowry acid on the reactant side is considered the conjugate base on the product side. And what was considered the Bronsted-Lowry base on the reactant side is considered the conjugate acid on the product side. And so there's a special name for these pairs. They're conjugate acid-base pairs. So every acid is going to turn into a conjugate base, and every base is going to turn into a conjugate acid. And I hope you see that on the product side, if this reaction went in the reverse direction, it would be molecule HB that would be donating a proton, which would make it the conjugate acid. Okay, so the fully diagrammed reaction is going to always have an acid plus a base is going to give us a conjugate acid and a conjugate base. I abbreviate those Ca and Cb. So conjugate acid, conjugate base. Okay, so let's do some examples so you can see this in action. So for the first one, we have the reaction between phosphoric acid and ammonia. Now, I said earlier that ammonia we're going to consider a base, and the reason for that is because the nitrogen in ammonia has a lone pair on it. Phosphoric acid we're going to consider an acid because just based on the name and because it has 3 protons that it can technically deliver. So what happens? We label them ammonia the base, phosphoric acid the acid. We're going to donate a proton from the acid to ammonia. So if you look on the product side, you'll see that now we only have 2 protons, H2. which means that we have a charge of -1 overall. Phosphate, the anion, has a -3 charge. Protons have a +1 charge, so +2 plus -3 is -1. Then the ammonia picked up that extra hydrogen and turned into the ammonium cation. We also know the name for that. Ammonium is NH4+. In all of these reactions, the charges should be the same on the product side as they are on the reactant side. So reactants charge should equal the product's charge. You may have to balance the reaction to get that to be true, but it's already balanced here. So we've labeled on the reactant side the acid and base. Now we have to label on the product side those conjugate pairs. So the acid is linked with the conjugate base, and the base on the reactant side is linked with the conjugate acid over here. Now, how do I know which ones to link? Well, you want to link essentially the same molecules, right? The ammonium's not going to go with the dihydrogen phosphate. Ammonium's going to go with ammonia, and phosphoric acid's going to go with dihydrogen phosphate. So importantly, an acid donates a hydrogen or a proton, right? And in this example, the phosphoric acid lost a proton and the ammonia gained a proton. So in example 2, we have hydrochloric acid and hydroxide. Hydroxide, we know, is always going to be a base, right? This is always a base. Hydroxide's always a base. Hydrochloric acid's always going to be an acid. So an acid donates a proton. So the hydrochloric acid is going to donate a proton to the hydroxide molecule. So hydrochloric acid then turns into the chloride anion, and the hydroxide anion picks up that hydrogen and turns into water. So if hydrochloric acid is the acid, then that means that the chloride anion is the conjugate base. It also means that the water here is our conjugate acid. So a base always turns into a conjugate acid, and an acid always turns into a conjugate base. Okay? The HCl lost its proton to the hydroxide molecule. Let's do another example. So here we have lithium hydroxide and sodium hydrogen sulfate. Now, whenever you see these 1A metals, you need to remember your solubility rules. All 1A metals are spectator ions. That means they don't do anything. They do nothing. They just sit there. Ignore them. Rewrite those ionic formulas without the 1A metals. So rewrite ionic formulas without 1A metals. And so I did that here. I rewrote lithium hydroxide without the lithium. Lithium has a +1 charge. Hydroxide has a -1 charge. So I have to keep that charge there. Then if I take the sodium away from sodium hydrogen sulfate, I'm going to be left with a total -1 charge there, because hydrogen, this H+, has a +1 charge, and the sulfate has a -2 charge, which ultimately is going to give us a -1 charge there. So hydroxide's always going to be our base. Hydroxides are always bases. So we put a base there, which means that the other thing has to be an acid, right? Even if you're like, well, I don't know if HSO4- is an acid or a base. You know that hydroxide's the base. So the other thing has to be an acid then. It's always an acid plus a base. So since HSO4 is an acid, that means it's going to donate a proton to the OH-. So HSO4 becomes SO4 2-. This is our conjugate base. That means that OH- becomes, again, H2O, which is our conjugate acid, right? An acid always becomes a conjugate base. A base always becomes a conjugate acid. Acids donate protons. Bases accept those protons. Another example, we have sodium hydroxide plus nitrous acid. Again, you'll see that I have that 1A metal there. We know that all 1A metals are going to be spectator ions. So we're going to rewrite this without the metal. So we have hydroxide plus nitrous acid. We know that hydroxides are bases, so the other thing must be an acid. Acids donate protons, so the nitrous acid loses one of its protons and becomes the nitrite anion and also the conjugate base. The hydroxide base gains a proton again, becomes water. So this is our conjugate acid. So a fully labeled reaction, you're going to have a base and acid, a conjugate acid, and a conjugate base. That's what I mean by a fully diagrammed acid-base reaction. Another example, here we have ammonium chloride plus water. And you're like, ooh, that ammonium chloride looks pretty weird, right? However, thinking back to our solubility rules, we know that all ammonium compounds are soluble. Ignore whatever the anion is. In this case, the anion is chloride. So we're going to rewrite this as ammonium cation plus water gives us what? And so I've told you here that the ammonium's the acid and the water is the base. For our class, water will almost always be a base. And when it's not a base, I'll be very explicit about that. But just assume that water's acting as a base for our class. Water's pretty much always going to be a base. So we have our acid, we have our base. What are our products going to be? So since ammonium is an acid, that means it's going to donate a proton, which means it's going to lose a proton. So if NH4 loses a proton, it becomes NH3. Ammonia has no charge. Plus, if water gains a proton, it becomes H3O plus. Remember, the charges have to balance. And if you're like, well, why does H3O have a +1 charge? Then I challenge you to draw the Lewis structure for this. If you calculate the formal charge about this oxygen, you'll find that it has a +1 formal charge. That's why H3O plus has that charge. This is called the hydronium, Hydronium ion, the hydronium ion. Okay, so let's finish labeling our reaction. So ammonium was converted to ammonia, which is going to be our conjugate base. And the base was converted to the conjugate acid, our hydronium ion. Perfect. Final example. Here we have, what is this first thing called? Yes, acetic acid plus ammonia. So acetic acid, I mean, if you just hear the name, right, we're probably going to think that's the acid. And we know that ammonia is going to be our base. Why? Because of the lone pair on the nitrogen. So our acid's going to lose a proton and become the acetate anion, which we'll consider our conjugate base. And the base is going to gain a proton and become our conjugate acid, ammonium. Ammonium is pretty much always going to be a conjugate acid. And that is all we have today. Thank you.